Hello everyone. Today's topic of discussion is BJT biasing, a very important concept of analog electronic circuit. Let us quickly go through the contents. We will first learn what exactly an amplifier is, then what is BJT amplifier, what is faithful amplification, what is BJT biasing, things to keep in mind during the design of BJT amplifier, important relationships which need to be remembered, different biasing circuits, and the fixed bias configuration. Now, what exactly an amplifier is? An amplifier is an electronic circuit which increases the strength of the input signal. Now, in this block diagram, you can see this is the block diagram of an amplifier, and this is the input section. The input has a signal which is an AC signal, and it has some amplitude. Now, you can see in the output we have an amplified signal. Now, one thing you can see here, the shape of the amplified signal, the frequency of the amplified signal is remain unchanged, but the amplitude is increased. Next is what exactly a BJT amplifier. The basic function of transistor is to do amplification, that we all know. The input signal is given to the base and of the transistor, and the output is taken at the collector. Generally, in case of NPN or PNP transistor, the input is always given to the base terminal and the output is always taken at the collector terminal. Now, what exactly a faithful amplification? Now we learn what exactly amplification is, what is an amplifier. Now what exactly a faithful amplification? Now the process of raising the strength of the weak signal without any change in its general shape, that is called your faithful amplification. Here we have two figures. The first diagram is unfaithful amplification and the second diagram represents the faithful amplification. Now in the first diagram you can see we have an input signal which is of AC type. We have an output signal. Now in the output signal we have only positive part of the input signal. The negative part is clipped off. So such type of signal or such type of amplification is called unfaithful amplification, because few portion of the signal has been removed. In the second figure you can see we have an input signal and we have an output signal at the collector terminal. Now the output signal, the input signal is completely amplified and the full shape of the output signal can be seen at the collector terminal. Next is BJT biasing. Now the analysis or design of a transistor amplifier requires knowledge of both the DC and AC response of the system, because during the analysis of BJT biasing we supply two types of component, one DC component and one AC component. Now the analysis or design of any electronic amplifier therefore has two components, the DC portion and the AC portion. Now the superposition theorem is applicable in such cases for the investigation of the DC conditions, which is totally separated from the AC response. Now what exactly a superposition theorem is? When a number of forces are acting on a body, or you can say when a number of voltages are acting on a system, then the effect of each and individual voltage can be summed up to determine the overall voltage on the system. That is a superposition theorem. Now during the design of a BJT amplifier, few things we need to keep in mind. Now we must keep in mind that during the design or synthesis stage, the choice of parameter for the required DC levels will affect the AC response and vice versa. The DC level of the operation of a transistor is controlled by a number of factors, including the range of possible operating points on the device characteristics. This we will see in the next slide. Now once the desired DC current and the voltage levels have been defined, a network must be constructed that will establish the desired operating point. Now before we will design any common emitter circuit, we need to keep in mind few relationships. These few important relationships are VBE is equal to 0.7 volt. Depends if the transistor is made up of germanium type of material, then the VBE value will be equal to 0.3 volt. If it is a silicon type, then VBE will be equal to 0.7 volt. IE is equal to beta plus 1 of IB, which is nearly equal to IC, and IC is equal to beta times of IB, where VBE is base to emitter voltage, IB is base current, IC is collector current, IE is emitter current, and beta is current gain factor, common emitter current gain factor. Now what are the different biasing circuits? The different biasing circuits are fixed bias circuit, emitter bias circuit, which is also called as emitter stabilized bias circuit, voltage divider bias circuit, DC bias with voltage feedback, and the last one is voltage divider bias with 2 power supply. And fixed bias circuit is the most common type of circuit, or you can say the very easiest circuit among all biasing circuits. Now here is the configuration of fixed bias circuit. Now you can see we have an active element, or you can say a BJT is there. The base is connected with AC input signals. The collector is connected with output AC signal. We have a base resistor connected at base terminal and a collector resistance connected at collector terminal. A DC supply of VCC is supplied, and there will not be any resistance or any passive component at the emitter terminal. So this is the configuration of fixed bias circuit. Now in the base terminal, the amount of current flowing is IB, and the collector resistance, the amount of current flow is IC. Now as we have already discussed, as DC as well as AC, both the voltages are acting on the circuit, we will go for DC analysis and AC analysis separately. So let us first go through the DC analysis. Now in the previous circuit we have seen we have used two capacitors C1 and C2. Those are coupling capacitors. Now during the DC analysis, the capacitor will be open circuited because the reactance of the capacitance is Xc, which is equal to 1 by 2 pi Fc, and for a DC signal the frequency is always equal to 0, and Xc will be equal to 1 by 0, which is equal to infinite ohm. So if the resistance will be infinite, the amount of current flow through this path will be equal to 0. So this path can be open circuit at the input side and as well as in the output side. Now in this circuit you can see we have two sections, input section and output section. So 2 kVL can be applied for the input and for the output. Now if you will apply KVL for the input section, then the equation will be VCC, the starting voltage is VCC, move around the loop. The next drop is IB current into RB, VCC minus IBRB, minus base to emitter voltage drop VBE, which is equal to 0. Now we need to find out the value of IB current. So IB current will be equal to VCC minus VBE by RB. Now you can put the value of VBE, which is 0.7 volt for silicon type of transistor and 0.3 volt for germanium type of transistor. Now this is a current equation which is very easy to remember. Now let us apply KVL in the output section. Before that, let us calculate the value of IC, which is a collector current, or you can see the IC current at quiescent point or operating point. Now ICQ can be calculated as beta into IB. Now for the determination of VCE voltage, we need to apply KVL in the output section. Now start from VCC, move around the loop, VCC minus ICRC minus VCE equal to 0, and finally VCEQ equal to VCC minus ICRC. Next thing, we need to calculate the saturation value or the maximum value of VCE voltage and IC current. Now from the output loop, we know VCC minus ICRC minus VC equal to 0. Now if you want to find out the saturation value of VCE voltage, then you have to put IC equal to 0 milliampere for an ideal condition, and the saturation value will be equal to VCC. Now if you need to calculate the saturation value of IC current, then in the current equation you have to put VC equal to 0, then the IC set will be equal to VCC by RC. Now let us define the operating point on the VI characteristics. Now let us see what exactly a VI characteristics. It is a voltage versus current graph, or you can say output voltage versus output current graph of a common emitter configuration. Now VCE voltage in volt, which is an output voltage, IC voltage which is taken in y-axis in milliampere. Now let's locate IC set or IC max and VC set or VC max on the graph. Now join these 2 points with the help of a straight line, and this particular straight line is called the load line. Now again draw the IB curve, which is a parabolic curve. Now the intersection point of load line and the IB curve is called the Q point or quotient point, or you can say operating point. So the coordinate of this Q is VCEQ, ICQ, or the operating value of VCE voltage and IC current. Now if a number of IB currents are there, IB equal to 0 microampere, 10 microampere, 20 microampere, and so on, then the shape of the graph will be like this for different values of current. Now depending on the value of current, depending on the value of IB current, the location of the operating point will be different, of course. Now when you draw the straight line connecting IC max and VC max, then definitely we will get different operating points. Now here we have shown few operating points: operating point at A position, operating point at B position, operating point at C position, and operating point at D position. Now it always depends on the designer which operating point they would like to select. Generally, this region is called the cutoff region of VI characteristics. This region is called the saturation region of VI characteristics, and this particular region is called the active region of the VI characteristics. Generally, the operating point must be chosen in the active region, which is much desirable for the faithful amplification. Now let us understand the fixed bias concept with the help of one numerical. Determine the following for the fixed bias configuration. Now we have a fixed bias configuration and we need to find out these parameters: IBQ, ICQ, VCEQ, VB, VC, VBC. The supply voltage is given plus 12 volt, RB resistance is given 240 kilo ohm, RC resistance is given as 2.2 kilo ohm. The coupling capacitors are given C1 and C2. Beta value, which is the common emitter current gain factor, is given as 50, or it is mentioned in the data sheet. Now from the input loop we know IBQ is equal to VCC minus VB by RB, and assuming the transistor is of silicon type, we can write VB equal to 0.7 volt. So 12 minus 0.7 by 240 kilo ohm is equal to 47.08 microampere. Now ICQ can be calculated by the formula beta times of IBQ, which is 50 into 47.08 microampere. 2.35 milliampere is the ICQ current. Now we know ICQ is nearly equal to IE. So IE current will also be equal to nearly 2.35 milliampere. Now from the output loop, we know VCEQ equal to VCC minus ICRC. We have already calculated IC value, RC value is given, VCC is given. So the VCEQ will be 6.83 volt. Now next is we need to find out VB voltage or the base voltage. Now we know VBE equal to 0.7 volt, and in this figure the emitter voltage is equal to 0 volt because the emitter terminal is directly connected to the ground. So VE voltage is 0 volt. Again VBE equal to VB minus VE. So finally VB equal to 0.7 volt. Similarly, VC voltage can be calculated by the formula VC minus VE, which is equal to 6.83 volt, as VE voltage equal to 0 volt. Now what is the value of VBC? VBC can be calculated as VB minus VC. VC we have already calculated, and VB is 0.7 volt, and the result is minus 6.13 volt. So this particular result is very interesting. The negative sign revealing that the junction is reverse biased, as it should be for linear amplifications. We have a condition for linear condition. The base emitter junction must be forward biased and base collector junction must be reverse biased, which is a condition for linear mode or linear region. Now let us find out the saturation value or maximum values of VC and IC. Now VC is set can be calculated by keeping IC equal to 0 milliampere. The result is 12 volt. IC set can be calculated by keeping VC equal to 0 volt, and the result is 5.45 milliampere. Now let us put all these values on the graph. So IC set is 5.45 milliampere, VC set is 12 volt, and the line joining is the load line. IB current is 47.08 microampere, and the intersection point is the operating point VCE and IC, which is 6.83 volt and 2.35 volt. Now you can see the Q point, the location of the Q point is on the active region, and this particular region is desirable for the amplification. Now let us see what are the advantages and disadvantages of fixed bias circuit. The advantage is the design is very simple. The circuit design is very simple as very less number of components are used. And due to the less number of components, the equations are very less complex also. So these are the two advantages of fixed bias circuit. Now what are the disadvantages? Operating point may vary due to the temperature variation, or you can say less stable. Amplification of an amplifier is not always the motto of a designer. We need to think about the stability of the circuit also. So stability plays a very important role while you design an amplifier circuit. Now you know IC is equal to beta times of IB plus ICEO, where ICEO is the leakage current for a common emitter circuit, which is collector to emitter current with base open. Now with the increase in temperature, or by any chance if the temperature of the transistor increases, then the beta value increases. If beta value will increase, IC current will increase. And if IC current will increase, the Q point may shift either towards the saturation or towards the cutoff. In the same way, in any case, if leakage current increases, then again IC current will increase, and the Q point may shift either towards the saturation or towards the cutoff. And we know, as we have already discussed, the best region for the amplification is active region. So any kind of temperature variation will definitely increase the instability of the circuit. So this is all about BJT biasing and the fixed bias configuration. In our next lecture, we will understand about the emitter bias configuration. Thank you.